So the triboelectric effect describes the electric charge transferred between two objects that come into contact. So I know I've experienced this because I have long hair. When I've brushed my hair with the plastic comb, it seems to create some sort of electricity between my hair, and my hair starts to like spread out far. It's pretty crazy. I've done it with a lot of my little cousins as well. Um, I brush their hair and then I can get them to laugh about it later on. So there's also the scalar field versus the vector field, and here I separated them, the scalar field on the left and the vector field on the right. So the scalar field is a single numerical value assigned to each designated point. It's one dimension with no orientation. It includes mass, electric charge, temperature, and distance. A vector field, on the other hand, is a value with magnitude and direction. You guys may have remembered that I put in the picture of Vector from Despicable Me, and he does say that his name is Vector. A magnitude of value with magnitude and direction. So this is a two-dimensional entity, including magnitude and direction, as I had just said, but it also includes displacement, velocity, and magnetic field. So we talked about friction, conduction, and induction. Friction is the resistance that one surface or object encounters when moving over another. So we did see this in one of our first labs with the rod and the little towel. Conduction is a process by which heat or electricity is directly transmitted through a substance when there is a difference of temperature or electric potential. Induction is a little bit different than both of them because it's a process of generating electric current in a conductor by placing the conductor in a charging magnetic field. And then finally, we have Coulomb's law, which is Newton's third law, that every action has an equal and opposite reaction. And then here's a little diagram to kind of show you what's going on. Thank you.
Very good. Thank you. It was a good review. Actually, this is a good idea for those students that have not presented yet. So maybe they could create a presentation that, review most of the topics that we covered in class. Very good. There are a couple of new students that just joined here. Let me just check here the roster. Um, let's see who else just joined the class. Ruby, Valentina. Okay, very good. Is there anybody else?
I could review one of my old presentations.
I can
If you-
present too.
Yeah, if you could do it now, okay.
Yeah.
So
I just have to join in through my laptop and then share from there. So
okay.
whoever else was, actually I can do it real quickly.
Very good.
Can you hear me? Can you hear me, Professor?
Yeah, I can hear you.
So this one, it's a shorter one that I made, but it's from last month. I believe this one's on electric energy and electric potential. So electric potential is energy that is stored and released by an electric potential difference. The amount of electric potential energy per unit of charge at a particular point is in electric fields. The work done by an external force to move a point test charge from a reference point to that point without acceleration. There's a difference between electric potential energy and electric potential. Electric potential energy, the energy stored in the system due to position of a charge is an electric field and in an electric field. If we place a positive charge in the field of another positive charge, there will be potential energy because of a repulsive force between the two. Electric potential, this is the amount of electric potential energy per unit charge measured in volts. It tells us how much energy would be needed or released to move a charge in an electric field. The difference between the two is the main difference is an electric potential represents the amount of work needed to move a unit positive charge to a specific point in an electric field, while electric potential energy is the actual energy stored by a charge due to its position within the electric field. Electric potential is a property of the field itself for describing how much energy per unit charge is available at a certain point. Electric potential energy depends on both the electric potential and the actual charge placed at that point. And electric potential is a scalar quantity. It doesn't have direction, but has magnitude. Electric potential and electric field. Electric potential around a positive charge decreases as you move away from the charge. It has magnitude in no direction. Electric field around a positive charge is a vector and points radially outwards and decreases in magnitude as you move away from the charge. It is a vector, meaning it has both magnitude and direction. And then for potential work and force, here are just the symbols and some of the formulas. For potential is V energy per unit charge at distance, R due to Q, and W is total energy required to move a charge Q to point Q, and F is the push or pull experienced by a charge Q due to the electric field from Q. And I think that's all I have.
Very good. You need to stop sharing. Canal, you need to stop. Okay, good. So Evan is going to do next. Charles, right?
Yeah, I can do mine. Okay. So this is a pretty crude and simple one, but it's of talking about semiconductors, which we talked about on 1015. I think that was 2 classes ago. So the first thing I'm going to talk about is AC and DC power. So DC current is the type of current used for everyday appliances, like plugging in your phone. It's one directional and not as extreme in voltage compared to AC. And AC current is the type of current that is in power lines that goes to businesses or to like bigger appliances, like big fridges that don't take DC power. It's 2 directional and usually very high in voltage. And a visual to help explain the directions of the currents is these 2 graphs where you can see that DC is one direction and alternating current moves back and forth. Semiconductor materials are different from both insulators and conductors. They have similar and different properties to both, but here are some properties of semiconductors. So semiconductors increase in conductivity with an increase in temperature, which is different from the opposite of conductor materials. Semiconductors can become more conductive when impure, which is also different to conductor materials, which usually become less conductive as they become more impure. And semiconductor elements are more or less conductive than other semiconductor elements, depending on how big or small their p-n junction is, which is the p-n junction also is like the band gap. So the bigger the band gap is, the harder it is for electrons to pass from the valence band into the conducting band. And if they're not in the conducting band, then you can't conduct electricity from that material. And then semiconductor types, there are two different types of semiconductor materials. P types have holes of electrons in the material that have a desire to fill the holes. The easiest way that I remember P and N type, which one has holes and which one doesn't, is that P is positive, so it has less electrons, it has holes of electrons, and then N is negative, it has spare electrons, it has more electrons than protons. And N type semiconductors have spare electrons in the material, which have a desire to be placed in a hole. So that was my
That's good.
quick.
Very good. Yeah, it's very important to do these activities, presentations, because, you know, it's like a refresher and remind people, you know, about the topics that we covered. Just keep track here of attendance.
Can I present next, Professor?
What's your name?
Esteron, last name, and first name Iris.
Yeah, I have you. Let me call names that that I don't have it here. Check. Valerie, is Valerie there? Lansley, is Lansley there? Adrian, are you there, Adrian? Natalia, Natalia there? So those are the 4 students that I do not have checked on the roster. Okay, everybody else.
Professor, did you put my name down? I just joined.
Valerie, let me just check. Yeah, Valerie. Yeah, okay. Thank you for letting me know you're here.
Thank you.
So again, Lansley is not here. Adrian Ramirez is not here, and Natalia is not here. So 3 students didn't show up today. Okay. Just I don't know if I hear correctly or not what Charles just said concerning the semiconductors. The band gap, it's something that all semiconductors have, independent of the type. If you know, if it's N type or P type, you know, depending on the impurity, even the intrinsic semiconductor has a band gap. The band gap does not show up when you make a PN junction. A PN junction is the interface between 2 different types of semiconductor. The PN junction has a depletion region, right? It's not a band gap. Depletion region is different than the band gap. The band gap is the region where electrons cannot exist, right? So the electrons are either on the valence band or the upper band that we call conduction band, where electrons are basically free to move. Okay, but the band gap is not something that shows up when you have a PN junction. The PN junction happens when you connect 2 different types of semiconductor, N and a P type, and then it creates a depletion region, okay, where, you know, there are no free charge. Is that okay? Is that what you said, more or less, Charles, or?
Yeah, I think I might have confused PN junction with the band gap. So
yeah, I just want to make sure that people, you know,
yeah, no, that's good.
understand that. Okay. Thank you for doing that. So let's start with the topic today. Let me just share here my screen. So again, this is your, if you look at your name and you see a bunch of yellow tags, that means you gave lots of presentations. If you see your name with the green tags, means you participate in class, giving, solving problems. If you see a purple, means you didn't show up. If you see purple with an X, means that you didn't show up, but you kind of justified your absence. Okay. So I just want to make sure you guys see that. So let's what's happening? Okay. All right. So let's move on with our presentation today. I have a short video that I'm going to show you right now. It's about one set up an experiment, and the wire is going to be moving here, and I want you to take some time to explain. If you feel it's necessary to make drawings to try to understand what's going on, please do that. And whatever you write, document that. Remember, this is a reflection activity, right? It's what we call, productive failure activity, that you have to write down your reasoning on an initial ideas of try to explain whatever, you see or I ask, or a concept, or, in this case, is somebody is doing this experiment, and the wire is going to be moving. And I want you to try to explain what happened based on whatever you learned so far. It's not for you at this moment to be completely, correct on your description, but to make, detailed description of what are you thinking right now, is causing this. Okay, so let me share now that is, I'm going to turn it on so I can repeat a couple of times. So are you guys able to see the design and, pay attention to details?
Yeah, we can see.
Okay. Okay. So again, I just want to make sure that everyone understand this assignment. I might seem kind of repetitive in saying these things, but my impression is that many students think that when I pose a problem, they need to come up with the correct answer at first. This is a problem that probably you have not seen this before. Maybe you do. Maybe you already know how this problem works because you saw somebody explaining to you, or maybe you already know the principles, the physical principles involved there, and you can figure out. Or maybe you have no idea what's going on. This um, assignment and activity is really for those ones that don't really know, what's going on there, right? And this gives the opportunity for you at first to be creative and come up with a model, forcing you to think about a problem that you don't know how to solve it first, or have not seen somebody solving, or you don't have all the foundation to solve the problem. See, this is the whole purpose of this kind of activity, is for you to make an effort and develop your creativity. It's a strategy to develop creativity, to think about a problem that you have not seen being solved before. Okay, so the second part is going to be, we're going to discuss, and then you're going to understand, based on physical principles, how it works. And then the most important part later is going to be your reflection about that. So as you do this, and you need to post those answers, all three parts on your portfolio, and all the grades, your grade is going to depend on this, on these activities, plus the presentations. Okay, so if somebody came up with some idea how that works, and why the wire is moving, I'd like to hear. So Charles, do you have some idea that you want to share?
Yeah, I can try. So well, how I thought about it was, I just thought about it as a circuit. So there's a copper wire, a battery, and a magnet. If it was just like the copper wire and the battery forming a circuit, there wouldn't be any movement because we've already done stuff like that. There wouldn't be any like angular acceleration. So I attributed the acceleration to the magnet. I don't. I just took a guess at why the magnet produced the acceleration, but I thought it had something to do with electrons moving through its magnetic field. That's just a guess, but yeah.
Very good. Anybody else?
I can
Want
try,
to share?
Professor.
Okay.
I actually did this as like a child's activity at my job. So if I'm not mistaken, it kind of creates like a magnetic field because the copper wire is kind of like a conductor, or it is a conductor. So it creates like a electrical current for the wire to interact with the magnet. And then that's what makes like the copper wire look like it's kind of like dancing or moving around the battery. And yeah, that's how it creates like a kind of like a current flowing.
Yeah. Very good. Anybody else? And when you write down all your ideas and maybe drawings, because the drawings sometimes in physics we used a lot drawings to try to explain things and problems. It helps to visualize sometimes what's happening. So if you do that, make sure you document that and leave it there. And then later, once we understand and go over the lecture, you can correct, on part 2 of the assignment, right? You write down make the drawing that is more accurate to the model that we're going to discuss and try to explain what's happening there. Is there anybody else that would like to talk about?
Professor, I can try it.
Good, very good. Go ahead.
Let me, if I can share a picture of it.
Right, go ahead.
Okay. Do you guys have my picture?
Yeah, I can see your picture.
I can see.
Yes, it's a schematic picture of this model. I think we have a battery here. Do you see my point mouse?
Yeah, I see your
Yeah.
battery.
This is a battery, and we have a circuit. It's separate from the magnet. Magnet is here to connect the negative the negative source of the battery to the wire. And and other reason of the magnets there to create a field near the wire. Let's say in other way, we have a current. We have a current in the circuit. When we have a current in the wire, uh, the field created around a wire. As current go around in the wire from here and from here to the negative of the battery, and it it is the reason to create a field around the wire. And we have the magnet separate of it, that the magnet has its own field, and these two fields uh, repel each other. And this is the basic schematic of something like motor, like electric motor. I think this is the reason of turning around of this wire.
Yes. Yeah, very good. Very good. Thank you. Thank you for sharing. So you need to stop sharing? Very good. Thank you. Okay, so so I hope everyone else has done something related to that. Okay, the part one of this assignment. So now we're going to proceed with the lecture. So hopefully it becomes clear as we go. So key points to explore here, so when something is moving, so it implies that there must be some forces acting on the wire, right? The wire is there, is free to move. And, it's like a cart sitting on a desk. If we don't apply any force to it, Newton's first law, remember, if there is no force being applied to this object sitting on the table, the object is not going to move at all. In order to start moving, you have to apply a force, okay? And when we apply the force, it starts moving. We're dealing with, electricity here, and, then we have, certainly we have electric current going through the wire because we connect the positive and negative side of the battery. The battery has a differential potential, and with that, it's going to produce a current on the copper wire. So what kind of physical laws explains this motion? And it could the direction or strength of the current or the magnet position affect the wire movement. Why or why not? So here, it's kind of a question. If I increase the strength of the magnet, and you saw that the magnet have was composed of different pieces, right? You put several pieces together. If I keep increasing that, the magnet field is going to be, the more magnets I have connected, the density of the magnetic field is going to increase. And the question is, how is that going to affect the motion of, of the wire, and if I increase the voltage also, how is that going to affect, the wire? So if you could, design an experiment, what would be the experiment to test those things, right? One is, can I change the magnet, and change the strength of the magnet? If I can change the current going through the wire by increasing the battery, maybe put another battery that is higher in voltage. That battery is 1.5 volts. Maybe you could put a 6 volt battery, and see, how that would work. And also you could change, the orientation of the magnetic field by flipping, the magnet, its position upside down. What do you think would happen? Would the motion change somehow? So would be a good exercise for you to think about those things. And if you're able to answer all these questions by the end of today's lecture, that you can feel yourself understand that you understand the topic that we're covering today. And that you could reflect on real-world applications. Mohammed already gave kind of a hint that this is like how electromotors work. So that's one application. So, but there are other applications, right? That you could use these physical principles that are involving magnetic field and electric currents. So this is something we covered last class, right? That the north and south attract itself, and north repel. Then I had this question. I posed this question last, but I did not show the answer. So if a magnet is cut in half, how does this affect the magnetic strength and the distribution of the magnetic field? So so cutting a magnet in half will actually reduce its strength, but does not necessarily reduce its strength by half. Okay, so this is important to understand. The exact effect depends on various other factors, right? When you cut a magnet in half, each piece becomes like a new magnet, right? You cut in half, now you have two magnets, right, with a north and south pole. So it's kind of demonstrated here, described here on your left. You have a bigger magnet, you cut in half, and then now you cut in 4 pieces. Each one of those has a north and south pole. The magnet strength and at the poles of each smaller magnet may appear weaker because the magnet's overall size of the surface have been reduced. However, the strength per unit of area of the magnetic field may not change drastically. because that is actually a property of the material itself, the strength per unit of area, So shapes may affect, um, the the magnetic field. Okay. All right. So let's move to the next slide. There was other questions too. What reduces? What actually is going to affect the magnetic field? So let's see here. So you supposedly you had this first attempt to answer these questions from last Tuesday, right? So now you having now part two. This is part two of the assignment, and then the part three is going to be for you to make a reflection on your initial thoughts. Don't focus when you do a reflection. That's another thing important that I notice when students do this activity is that on the reflection, you focus on the part that you are right? That's not what I suggest you to do or I would like you to do. What I want you to do is to focus on the part of your answer that was not clear or was a misunderstanding, because focus on that is going to enhance your understanding of the topic. If you focus on the part that you were that you thought was matching the right answer, then there is no learning process done there. So this kind of reflection activity is really to enforce, and focus on things that you misunderstand. So you do an effort to understand, the principle, and try to understand your initial ideas, okay, better, where they're coming from, and finding the root cause of that. That helps and improving your understanding. So there are external factors, that besides the fact that the different materials, they have different properties. You can reduce the magnetic field by temperature, right? Curie temperature is the temperature that the magnet is being heat up to a certain point that completely loses its magnetism. So this is a property of magnetic materials that if you increase temperature, it comes to a point that they are not magnetic anymore. So physical damage, repeating striking or dropping can disorganize the alignment, because magnetic properties are based on alignment of the atoms inside the material. They all align in one direction, so that creates this magnetic effect. And when you increase temperature, this alignment is disturbed. When they fall on the ground, so if you have a magnet that you purchased and you let the magnet fall, so it's going to start losing its magnetic properties. So you got to be careful not to let it fall if you want to keep strength of the magnetic piece that you have, right? Also, when we learned actually last class that we can magnetize, a nail, right? We had a strong magnet on the table. We went there and we exposed that nail to this strong magnetic piece there, and we learned that eventually the nail was able to become somewhat magnet and attract other piece of metal, like paper clips, was small enough and light enough that I could try to attract it. So that means exposing, ferromagnetic materials like iron to a strong magnetic field can create some sort of temporary magnet, But if you do the same to already existing magnetic material, right, and the opposite, direction, it can create a disturbance and desmagnetize, uh, uh, cause a lack of alignment, within the atoms of the material that is going to lose its properties. Is that okay so far?
Yeah.
Good. So now about cutting the area, we kind of already talked about. So once I post this on the this PowerPoint on Canvas, you'll be able to retrieve these answers and go on. So let me move on to the next slide. This is a little, the link is here of this activity. The child was doing some experiments. We did this last class. So here again, some way to magnetize. This is something we did in class with this little bar here could be the nail that we exposed to some magnetic field, and then the action on heating, or tapping that could, eventually destroy the magnetic field. Now here it's visualization of what's going on inside, piece of iron, for instance. They have different regions. They are somewhat aligned, but they all, randomly distributed. They're not, being forced to align themselves. And as I expose them to a strong magnetic field, they move from one situation to the other one. You see here on the right, on the left, far left, you see here everything not very organized, right? And on the far right, you see everything in one direction. So I'm not trying to be political here, but it's not, this is just physics. But I'm just saying that on the left, things are all over the place. But as I start, exposing them to some very strong, magnetic field, they start to align themselves, and then, eventually it becomes a magnet, north and south in one direction. Uh, then here we have some of the Maxwell equations. It's not important that you memorize this for this course, but it's just trying to understand what they mean somewhat. Uh, uh, some of these descriptions here involves calculus, and this class does not require calculus, but this delta here, this kind of upside down delta, means variation, or rate of change. If I change the electric field, that is going to be direct related to a change in magnetic field. And this is somewhat kind of important to understand, because talking about the electromagnetic wave, it's called electromagnetic because it has both fields being acting together, that create this magnetic wave. The electromagnetic spectrum varies from radio frequency up to gamma rays, and in between we have, division spectrum, right? Light is an electromagnetic wave. So that, what does that mean? Well, it means that has, the electric field and the magnetic field, as means of transportation, moving from one point to the other. So talking about these things, it seems somewhat kind of abstract, but I found an excellent video, that the truth is, I kind of envy many of you because, nowadays, you have all these visualizations, that explain things that if we can see is somewhat very abstract to understand. So 50 years ago, when I was in school, as a student like you, I didn't have that. So I'm kind of amazed now how things are easy, somewhat easy to understand. So I'm going to share this video. That the link is here. You're welcome to revisit that. But one interesting thing here is that you noticed here the purple arrows here. They represent the electric field, and the green represent the magnetic field. And you see that they travel. A wave, is a way to travel, transport, or energy. It's not physically traveling, but it transfer energy. And you see that the maximum of the magnetic field, coincides with the maximum of the electric field, right? So the maximums, they coincide. And if you look at this equation here, you see that the rate of change of the electric field is proportional to the rate of change of the magnetic field. What does that mean? That means that if there's a little change in electric field, there is a little change in magnetic field. And as there is a larger change in electric field, there is going to be a larger change. So it's direct proportional. So that's what this represents, basically. Another thing is that this is a vectorial, vectorial product, right? Here, it's a vectorial product. So there are a vectorial product is perpendicular to the end result here. If you guys remember when we were discussing in a different class, a torque, distance, right? Displacement versus, the force, the torque is the radius. It is a vector, right? The position where the force is being applied times the force is torque, right? And the cross product, the vectorial product, of the position vector times the force is the torque, and that is a perpendicular vector, right? So you see here the vector product of the delta and the electric field, is going to result in a perpendicular vector, right? That is the variation related to the variation of the magnetic field. And so this is kind of described here, but you can visualize here also. So now let's see on the video the description of how the electromagnetic wave is generated by an electric charge. The motion of the electric charge going up and down. So let me share this with you. So this is, I'm not going to show the whole video because, it's like 20 minutes. I don't want to take all that time, but I do encourage you to revisit this and watch the whole video. It's
vector, which is perpendicular to the line drawn between the two charges. In other words, when you wiggle that first charge, the direction that the second charge wiggles is always perpendicular to the line between them. And the amount that it wiggles gets weaker and weaker when that line between them is more lined up with the initial acceleration. As before, this is something you might see written down in a way that describes a component of the electric field caused by just one charge. Again, that means what force would be applied to a second charge at all possible different points in space. This component of the field is only ever non-zero when our first charge is moving somehow, when it has an acceleration vector on it. And because of this delay term, the effects on this field tend to radiate away from the charge. This is why I'm writing it down with the subscript rad. This is the component of the electric field that will radiate away from a given charge. For instance, when the charge is oscillating up and down, you get these propagating waves. And for many of the vector fields I'll be showing, the intensity of the field is illustrated with the opacity of each little vector. This radiating influence is light, or more generally, electromagnetic radiation, including things like radio waves and X-rays and all that good stuff. As a side note, you sometimes see this propagation described a very different way that puts the fields front and center, using what are known as Maxwell's equations. For our purposes, I want to focus just on this one law and show just how far it can take us when it comes to intuitions for light. For the animations I'm about to show, all I've really done is encoded in this one law, which tells us what should this component of the electric field be at every point in space, as determined by the history of accelerations of a particular charge. For example, if I set that charge oscillating up and down in the z direction, and illustrate this component of the electric field everywhere on the xy plane, you see these circular propagations of equal strength in all directions. It's a little easier to think about if we focus on just one axis, like the x-axis. And at first when I made this animation, I assumed that there was some kind of bug, because near the charge it just looks crooked and wrong. But when you think about it, this is actually what you should expect. Because remember, each one of these vectors is supposed to be perpendicular to the line drawn between that point and where the charge was at some point in the past. At points that are far enough away from the charge, which is where this component of the field is what dominates anyway, the wiggling in the field is essentially parallel to the wiggling in the charge, which is why when we think about light waves, we're safe to think about the wiggling direction as being perpendicular to the propagation direction. Like I said, this propagation for just one charge is equally strong in all of the directions perpendicular to its wiggling. And really, I should emphasize that the propagation does happen in all directions of three-dimensional space. It's maybe a little busy to try to illustrate the full three-dimensional vector field on screen like this, so it's clarifying if we just focus on, say, the xz plane. Notice how the waves here are strongest in the x direction, but it still does propagate in all other directions. It's just that that propagation gets weaker in directions that are more aligned with the original wiggling. At the extreme, the only place where there's no propagation is in the z-axis. Because our law has this 1 divided by r in it, the strength of the wave caused by just one particle does decay as you go farther away, in proportion to 1 over r. But notice what happens if I take a whole row of charges, say oriented along the y-axis, and I have them all start wiggling up and down in the z direction, and I illustrate the combined effects that all of them have on this component of the electric field. The effects of all these charges interfere deconstructively along the y direction, but they interfere constructively along the x direction. This is what it looks like for a beam of light to be concentrated along just one dimension. So if you were to focus on the field just along the x-axis, instead of decaying in proportion to 1 over r, this combined effect decays much more gently. In the extreme, you can get something arbitrarily close to those pure sine wave propagations we were illustrating earlier, if at some distance away you have a large number of charges oscillating in sync with each other like this. One thing that's worth emphasizing when you see light illustrated with a sine wave like this is that even though that wave is being drawn in 2 or 3 dimensions, it's only describing the electric field along a one-dimensional line, namely the base of all those vectors. It's just that to draw the vectors, you have to venture off of that line. Great. So one of the last important things to highlight before we get back to the sugar water is polarization. In everything I've been showing, the driving charge is just oscillating along a single direction, like the z-axis, and this causes linearly polarized light. But it doesn't have to happen like that. For example, if I set the charge rotating in a little circle along the yz plane, meaning its acceleration vector is also rotating in a little circle, notice what the field looks like. This is known, aptly enough, as circularly polarized light. Honestly, it's easiest to think about for just one point of the electric field. What it means for light to be circularly polarized is that at that point, the electric field vector is just rotating in a circle. People often find circular polarization a little confusing, and I suspect part of the reason for that is that it's hard to illustrate with a static diagram, but also it's a little confusing when you try to think about the full electric field. For example, here's what the field looks like on the xy plane when I set that little charge rotating in a circle. It's certainly very beautiful, I could look at this all day, but you can understand why it might feel a little confusing. The very last thing I'll mention is that while everything here is a classical description of light, the important points still hold up in quantum mechanics. You still have propagating waves, there's still polarization that can be either linear or circular. The main difference with quantum mechanics is that the energy in this wave doesn't scale up and down continuously, like you might expect. It comes in discrete little steps. I have another video that goes into more detail, but for our purposes, thinking about it classically is fine. Part of the reason I wanted to go through that is because, frankly, it's just very fun to animate, and I like an excuse for a fundamental lesson. But now let's turn back to our demo and see how we can build up an intuition for some of our key questions, starting from this very basic premise that shaking a charge in one location causes a shake to another charge a little bit later. And let's start by actually skipping ahead to question number 3. Why do we see the diagonal stripes?
Okay, so let's move on. Um, so one thing is important to notice, to remember, is that the atom itself, we discussed that when we were talking about semiconductors, that the atom itself has a spin, right? It's not necessary that the atom is kind of rotating along some axis, but on the classical way of thinking. But that the atom is itself a little magnet, right, with a northern pole, uh, you know, model, right, the way to visualize it, and that creates the magnetic. So currents are related to this, source of magnetism. Okay, so two different models, that we have. It's what is called the planetary model of the atom, that an electron is orbiting the nucleus, forming a closed loop. So the current, the motion of electrons produce the magnetic field, the northern pole, and the other model is that the electron itself, has this spin that, that forms the magnetic field. So the truth is neither of them, is completely consistent with the, with the, what's happening in reality, but they do explain, the phenomenon. So there are some, simulation activities that, I think helps to visualize, things like, this one here. You can, you can see inside the magnet, alignment inside the magnet, and you can see that, the strength, um, the strength changes, right? If I put it here, I can see measurement of 14, but as I go further away, I see the numbers here going weaker and smaller and smaller, right? You can, see that. So that's one thing to keep in mind. The other one here is this other activity here that right now nothing is happening. We do have a magnet. The magnet is not moving. The coil itself is not moving, and there is no current. You see the light bulb is not turned on, right? If we want to turn the light on, we would have to apply some motion here, right? And actually apply some work, do some work so we can convert that into electricity and light the bulb. So let's see if I open here this uh, waterfall. So the water is falling. So what's happening now? The magnet is moving, going around, and what's happening now is that the current moves in one direction, then moves in the other direction. So the motion of the magnetic field on 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 um, on the charges that are inside the free electrons that are inside the conductor now create a force on the charge itself. On the previous example, we had a magnetic field. A current was moving, and the magnetic field was fixed. On that the initial experiment that I showed with the battery and the magnetic, field at the bottom of the battery. So that was a fixed magnetic field there. The magnetic field was not changing at all. But once I applied the current, right? It created a little motor, right? So the things start moving. So because I'm applying the current here, instead, what's happening is I'm not applying the current. I'm applying, a change and causing the magnetic field to change. So what it does is generating, a current. So this would be the principles of generating electricity instead of using as a motor, right? So what would happen if I closed this valve here and now I just let the magnet sit there, but this is still a wheel that can rotate. But what I do instead of I replace this lamp by a battery. So now what I'm going to have here, I'm going to have moving charge going around. So the moving charge are going to create a magnetic field that is going to interfere with this magnet, and the magnet is going to be moving. So so it's like a motor and a generator are themselves kind of the same thing. It's just that you change the um, you know, the different uh, activities, right? You either move the magnet or you have a current going through it. So one thing I want to emphasize also is that if I increase now the motion here, you can see that the light is getting stronger, and that's something interesting, to see also now that the increase in rotation, if I reduce it, so reduces the intensity of the light, now here I have the option also to change the number of loops. You see here I have 2 loops, right? Right now here I see number 2, and here on this description I see 2 loops going around. And but if I increase here to 3, So I also see an increase on the intensity of the light, right? So see, I'm going to reduce again now to 2. You see now the light is kind of weak, like on 1. And if I if I move to 4, then you see, an increase of light intensity, right? So I can also increase the area, here I see also, an effect on the light intensity, right? Smaller loops, right? Versus larger loops, you see that, affect also, the thing. I can also change here, you know, the strength of the magnet. So the magnet now, I put magnet 0, so it's not a magnet anymore. So if there is no magnet, you can see that there's going to be no current, right? Now let's start increasing the magnet. Then you see a small, production of current, and the intensity is increasing. If I increase the mag to its highest strength, you see, that the density on the light has increased significant. All right, so let me go back here to the PowerPoint. Is there any question about? So those links actually are here posted on this slide, so you're welcome to go visit again and play with it yourself. I think they are part of the lab simulation assignment. Now magnetic field and magnetic field lines, right? You have here on B, you have here a wire, and the current is going up. And if you use your hand here, your right hand, and your thumb pointing to the current, and your fingers, going around the wire, they indicate, the direction of the magnetic field, right? So you see that one side on C, you see to the right, you see that right here, you see that, on your left of the wire, you see the magnetic field pointing towards yourself. And on the right, you see the vector of the magnetic field point to inside the screen of the computer. Also, if you have a loop, you see the magnetic field going around, with directions going up from the inside the loop and outside going around. Okay. Sometimes my computer gets stuck. Okay. So on this next slide here, we now, well, if something is moving, like the wire, is moving on the magnetic field, it's because there is a force. Now, how this force is calculated, you see here the motion of the charge, V, the velocity, of the charge itself, or the wire, right? When you move the wire on the magnetic field, so you have basically the conductor is, has charges, they're electrons, free electrons on a conductor. So when you move in one direction, it's going to be, a vector. and the direction of the magnetic field, is going to determine the force, right? So one thing to notice again is that this is a cross product, and here on the bottom on the left, I have a short kind of reminder here: what is a dot product and what is a cross product. When you think about torque, right? That is distance times force. If he is the cross product, right? The vector cross product, and that is torque. But if you do instead a scalar product, or what is called the dot product, then that's not going to be torque anymore. That actually is going to be work. So, I need to pay attention on these things. So vectorial is a mathematical description of what's happening in physics. So we have created this in order to explain torque, in order to explain work. Work is not a vector, so now the cross product is, if you want to calculate the magnitude of the force of a cross product of vector and magnetic field, you need to actually multiply the charge times the magnitude of the velocity times the magnitude of the magnetic field times the sine of the angle between them. Okay, and when they are in perpendicular, the sine of 90 degrees, the sine of 90 is 1. So when they are perpendicular, the product is just and it is the highest value, right? Because sine is of an angle it can be between 0 and 1. So when it is 1, so you have there a maximum, right? So it's the maximum force versus if the angle is not, is somewhat less than 90 degrees, then the force is going to be somewhat reduced. Now, so here, there is, is showing that, the charge of the, if I move a charge in one direction, the force is going to depend on the charge itself, right? So the force is, if the charge is positive or the charge is negative, it's going to change the direction of the force, okay? So, when you go through a magnetic field, so it's going to happen. Now, so also, as the force is, perpendicular to the velocity, so that is, if you can kind of make an analogy to when you have, an object on a piece, on a string, and you rotate circular motion, right? When you have circular motion, what makes the object goes on a circular motion is the centripetal force. It's the force, towards the center. So the magnetic force is a centripetal force because it causes the particle to go around, right? To curve itself. If a particle moves inside a magnetic field, the force is going to be perpendicular to its direction. So it's going to cause the particle to go on a circle. So so that's one of another thing to keep in mind. Now we use these things. This is an example here of an electron being accelerated in what we call the bubble chamber. to observe. This is an experiment to study elementary particles. So particles like electron are accelerated into this chamber that is transparent, but has very hot liquids like liquid hydrogen, and then they take pictures of of it. It's the bubbles, right? Because as the particle travels, it ionizes the atoms along its path and leave little bubbles behind. And here the experiment is an electron beam colliding with a gamma ray, very high energy. So it causes it to split into two other particles, right? So it creates a particle a pair, right? And so this is one. It's just to give an example of an application of a magnetic field, right? You can think, oh, magnetic fields can be utilized only to create or build a motor or generator, but there are experiments like instruments to measure things. They are based on magnetic field. So this is one of them. Another thing also that is that magnetic field creates is what is called the Hall effect. Basically, when you apply a magnetic field on a wire, right, and the electron is moving, the electron is going to see this force, right? The force is going to push the electron to one side of the wire, so it's going to create on the wire from one side to the other an electric field. Here on the left, you see this little, E here, right? The epsilon is this, creation of this electric field because electrons, due to the magnetic field, right? They being pushed to the bottom of the conductor, and that creates a positive charges on the top of the conductor, and this positive and negative, right, generates an electric field, and the measurement of this, is what what is called the Hall effect, and of course this is going to depend on on the moving charges of a fluid or anything like blood, for instance, right? Blood, has electrons, and you can make measurements of that as well. The Hall effect can be used to have what is this due to a magnetic field, what is going to be the measurement of this electric field is going to depend on the number of particles. So basically, a moving conductor here, if you see the conductor is moving in this magnetic field, is going to generate, a voltage, right? So, it conducts and generates a voltage. So here are some of forces that you can see. Again, this is the same formula that we saw before there. So it's just you use different parameters. You can correlate force with the current and the magnetic field. And here again, it's showing how actually a motor can work. You see the current going up, and the magnetic field is in one direction. Is going to develop a force on the left side, trying to move this loop towards this the screen, and on the other side, the current is going in the different direction. You see that here on the right side, the current is going down instead of going up. So it's going to flip the force. So there are two forces that are, causing, a torque, right? And that what makes, this generate a little motor here, right? And you can see here on the left again, the relationship, how this visualize the torque. So again, now instead of you can also when this thing is moving, it can produce electricity, right? Now here what you have is the coil is being moved by whatever means, could be the hydroelectric, potential energy of the water falling and making like a spinning, and that creates voltage. And you have here, like charging a battery, right? So the current is being produced and charging the battery. This is also principle of different meters, like, I remember first day of class, I showed, a way to measure current, that a big instrument, and that, certainly is, a coil that is inside with a magnet that, makes this needle move in one direction or the other, depending on the strength, of that magnetic field that's being generated there. So you're able to measure, the deflection of and make a scale, right? Calibrate, the instrument with a certain current. Now here is Ampere's law that correlates the magnetic field with current directly proportional to the current. So more current, you're going to have more magnetic field. So it's not necessary for you to memorize the formula, but it's important for you to see that the magnetic field is direct proportion to the current. So I increase the current, and you kind of saw that also on the simulation, that as I increase, the current, the intensity of the light, I increase the magnetic field, increases the current, and so the light. So this, again, it's showing that. Yeah, this is, you can visualize that with that simulation. Again, Ampere's law, also the right-hand rule to just to for you to visualize the direction of the magnetic field. Okay. Now, another application of the relationship between, magnetic field and electric current is a mass spectrometer. Mass spectrometry is based on the fact that, charged particles, as they are accelerated in a magnetic field, they're going to curve, right? And the curve, is going to depend on this centripetal force, right? The magnetic force that is being, acting on the particle, and of course that's going to depend on the charge itself, on the mass of the charge, So if you have an ionized ion on a molecule, or a different atom has different masses, and as it's moved inside this magnetic field, it's going to go on a circle, and that circle is going to depend, the radius of that circle is going to depend on its mass. So that's why, this is a mass spectrometer. So if I have some kind of element inside, and that I want to study. So I can identify, in some volume of some elements, which elements are inside that volume. So I have a volume that I want to identify different contaminants, for instance, and where are they? If it's argon, argon is a heavy metal. So if I have a chamber that is being somewhat clean, or has some vacuum, but there are still elements there that I want to know what kind of elements are there, so I can use a mass spectrometer connected to this vacuum chamber, and I'll be able to identify what kind of contaminants, because they're gonna hit a certain location in relation to the entrance, right? And I can measure the radius. If I have the radius of the location where that element is hitting the screen, then I can correlate that with a mass. So the mass is going to be proportional, directly proportional to the radius, right? So I can identify different elements. And our last slide is, again, now this is something we kind of discussed at the beginning of class, first class, about the cathodic, experiment, right? So now I'm assuming now you understand why, the magnetic field, causes the beam to deflect, and goes on a curve here, and hit a different point depending on the strength of that magnetic field. And it's going to affect the force. The velocity of the particle is in the direction of the screen, and if there is no magnetic field, it goes straight to what this one point. But as a magnetic field is being applied, then it creates a force that, if the charge is positive, it goes in one direction. If it's negative, it's going symmetrically to the other direction, going upwards. And so you can understand that now. So let me stop here, and let me stop. Is there any questions or anything? I'm going to stop the recording. So.